Welcome to this presentation, Using All Processor Cores While Being Confident About Timing. My name is Björn Andersson. So let's look at the big picture. The big picture is that we see many complex cyber-physical systems, and they are depending on correct timing, and this is widespread across the Defense Department. And we need to use multi-cores in these systems, and when we use multi-cores, it becomes more challenging to satisfy time requirements. And the common practice, what we've seen from many DoD programs, is that they want to disable processor cores except one, because that simplifies the timing verification. And the goal of this project is to develop a solution that overcomes this obstacle. So we want to be able to use all processor cores while being confident about timing. So if we look at the Defense Department, we see many systems like this. We see platforms that move in the physical environment. They interact with the physical environment, and they often should have an effect on the physical environment. And the way this interaction is achieved is through software. There is software in all of these systems. And so this software interacts with the physical environment through sensors and actuators. And in order to do this, it needs to satisfy hard real-time requirements. You can ask, why is that? It is because the software reads sensors, it commands, but before that, it performs computations based on those sensor readings to decide what the actuation command should be. And if the software is too slow, if the delay from sensing to actuation is too large because the software is too slow, then the actuation is based on old information. It's old news. And then you're acting on old news. And that can cause instability and control loops, but it can also cause other bad effects, like a countermeasure is not deployed at the right time. You may compute the right result, but it's not computed at the wrong time, so therefore the interaction is bad. For example, the countermeasure is deployed at the wrong time. So this is a challenge for the Defense Department in general, and the solutions that we develop are also general purpose technology for the Defense Department in general. But we've heard one specific program that's been on record with this issue, and that's the Black Hawk UH-60 helicopter. And you see that on the top row, the third from the left. And here you see a quote from a former director of AMERDEC, now it's called AVMC, that points out that we need to make sure that software produces data at the right time, and there's no room for error, and we want to use multi-cores, but that's problematic from time verification perspective. So what do these systems have in common? It is that we can look at it this way. You have a computer, we have a program, and if you look very carefully, you see that there's a while loop. You see a read sensor perform computation, actuate command. It keeps doing that over and over again. And then you see that what it does is that the sensor reading gives sensor readings, and the computer gets those sensor readings. And then when it computed actuation command, it sends those to the actuator, it influences the environment, and then it in turn influences the next sensor reading. So it keeps doing that over and over again. And so if you look at this from the time perspective, we can see here the timeline. Time goes from left to the right, and we see one event called read sensor and then the actuate command. And then we see that it does the same thing again, read sensor, actuate command, and again and again and again. I'm just showing it twice here. And now we see the characteristic. We see the period, which is the time from we read a sensor. So often in the DoD system, we specify things like this should happen at the rate of 100 hertz, therefore the software needs to do this at 100 hertz, therefore software needs to do it with a period of 10 milliseconds. And that's where you get this period from. And then also the deadline is another characteristic of the system for this program. The deadline is the required time from sensing to actuation. And sometimes we have more than one program, and then we end up with a sequence of these events, and then between these events we have computations, and then that computation will be interleaved, and because the number of programs may often be larger than the number of processors. So we end up with a scheduling problem here. So you can ask, why is it that satisfying time requirements is so challenging? If it was easy, then it would all be done, and we wouldn't have to do this research. So one way to answer this question about why it's challenging is to ask, why is it because of delays of software? And there are many reasons, and I'll just show some simple ones. So some scenarios with simple ones. So here we see progression of time going from left to the right. And we see one scenario when we have a single thread arriving and we have the deadline. In practice, this thread will arrive again and again and again. And in practice, we'll have many threads. So I'm just showing here a single thread and a single arrival. And then in a program, it can execute different paths. And the reason for this is that often programs are implemented in imperative programming languages. They have conditions that determine truth and falsity of conditions that are used in the if statement and while statement. That generates different paths. So different inputs to the program and different state of the program causes different execution paths. So here's one path. Here's another one. So the internals of the program can influence the execution time and the sensory inputs. Also, there is interaction between programs. So sometimes one program is preempted by another one, and that's what we see here. So there is some time here when the blue thread is not executing. And the reason for that is that the blue thread was preempted by or interrupted by another thread, which is not shown here. But during this time, the blue one is not executing. And then there's another effect where the blue thread is requesting critical section, and then that's maybe held by another thread, and then therefore the blue thread cannot execute. So here we see one scenario where the blue thread finishes very late, another scenario when the blue thread finishes very early. And what we're asking is, does it hold that for all scenarios the finishing time is before the deadline? So there are many other effects also, but this gives an idea of why it's challenging. But this, what I talked about so far, was about single core processors. Now let's talk about multi-core processors, because that's what we're focusing on, and that adds more challenges. So today, almost all computers are multi-core processors. And the multi-core processor is a chip with many processor cores, so you can have true parallelism, you can execute many programs simultaneously. And today, it's offered by almost all chip makers, and it's from most chip makers, it's hard to even buy single core processors these days. And there are different types of multi-core processors, but the common one is the one with shared memory. So shared memory actually means two different things. One meaning of the word shared memory is that you have main memory that's shared between processor cores. Another meaning is that you have a shared address space, a shared physical address space between processor cores. And in this talk, I'm making both of these assumptions. That's the assumption that's relevant for many of the DoD systems we've seen. So the problem we face ourselves now is that we have a set of processes or a set of threads, and then we have a set of processor cores, and we have some private resources for each core. You see L1, L2, and then we have a memory system shown in this gray rectangle, and then in this memory system we have shared resources like last level 3 cache, memory bus, memory controller, and the DRAM banks. And there are many other resources also. This is a simplified view. So we would like to have prove an upper bound on the response time for these processes. And response time is an upper bound of time from when it is requested to execute until it finishes the execution. So let's try to understand this a little bit further with one scenario. So here you see the same system again, but we look at it from a timeline perspective. So we have the 3 processor cores, one core, another processor core, another processor core, and then we have a red thread which arrives here. Arrives means that it's requested to execute. Then it starts to execute, and then it finishes, and you see the finishing here. And here I'm using the horizontal axis to indicate the progression of time, but I'm using the vertical axis to indicate the speed of execution. So how tall this is indicates how fast it executes. Now it executes at full speed because there's nothing going on the other processor core. It doesn't get preempted, and nothing going on the other processor cores. So there's no contention for read through the memory system. This is just one scenario. This is a good sunny case scenario. We have other scenarios too, and here's another one. So here, the red thread starts to execute, and then at these times, there's nothing going on the other processor cores. But then a little bit later, at this time, there is a green execution on the core 2. So now the green executes in parallel with the red one, and because of that, there will be contention for read through the memory system. So therefore, the red one executes a little bit more slowly. And that's what you see here, that the bar is not so tall as it was before. And then over time, the speed changes because there are different co-runners over time. So the speed of the red, execution of the red, varies over time because the co-runners that it experiences varies over time. So you see here, you get the longer finish time is later. So as I already mentioned, we have a shared hardware resource, the impact timing. You can ask, how bad is this? So it depends on the specific software system, and it also depends on the hardware, how many shared resources you have. But there have been reports in the research literature that you can experience 103 times slowdown. So it can be quite bad. You might run it first, it takes a millisecond, but then when you run it in another scenario, it's almost a second. And there's actually been reports that it can be even worse. And there's been reports about showing that it can actually be 300 times and even 1,000 times. But this is the most well-established reference, the one I'm showing here. And there are different challenges we are facing. One of them is that in order to satisfy time requirements and in order to prove that we meet time requirements, we want to prove a property. And then we don't know exactly how the system works. So we're trying to prove a property of the system, although we don't fully know how it works. And that's because we are undocumented resources. The reason is that chip makers do not disclose all the internal stuff about, for example, how the memory controller works. Some resources are documented, but some are not. So some of them we know how they work, and some of them we don't. So that's a challenge. But we also have a challenge that even if we would have good documentations, it's very difficult to create analytic methods to prove upper bound and response time for this software, considering these resources, because it's very complex. There have been previous academic work, we have done some of that, and we analyzed only a small number of these resources, and, because it becomes very complex. And then we also have the complexity that, the challenge that sometimes there are defects in the documentation. They're wrong. They say things that are not true. And this problem is getting worse. So we have a slowdown is getting worse because the chips have more and more processor cores, and we have more and more processor cores. It means that there's more and more processes that can execute in parallel. Since we have more and more processes that can execute in parallel, there'll be more and more memory accesses that are generated per time unit. And that puts more and more pressure on the memory system. The queues are building up, and that causes more delay for each request to the memory system. So that's why we get more slowdown. And since we get more pressure on the memory system, the chip makers are trying to implement new hardware features to deal with this. They implement new latency hiding techniques. For example, more level caches. Instead of having just 2-level cache, we have 3, or some have even 4. And they implement new prefetching units, new write-back buffers to try to hide that latency. And these extra hardware devices in the memory system, they are often not documented, and that increases more resources that are shared, and it increases the number of resources that are undocumented. That's a challenge as well. So we need a new method to compute response time of processes, considering this reality. So we have created many results in this project. I'm not going to go through all of them and all the technical details. I'll give an overview of our solution and how we can use this in the Defense Department. So we would like to ask a question. Does it hold that for all scenarios, for each task, all its deadlines are met? And then we would like to, that's an algorithm or procedure we would like to have. And we have developed that in the project. And that should output yes or no undecided. And ideally, we don't want it to produce the result undecided. But sometimes it's very hard to answer this question. So sometimes we produce the word undecided. But we would like it to produce the answer yes or no. And this is, in the literature, this is known as scalability analysis. That's a term of art in the research literature. And sometimes we do not just produce yes or no, we also produce the response time. If the answer is yes, it produces the response time. So you can actually see what is the upper bound for each thread on its response time. So here we have an algorithm or procedure that produces something, but it also needs some output. Some input. And what I'm showing now in this slide is activities that we implemented as tools, but I also show information. And the information is shown as gray rectangles. So one piece of information we need is a period of a task. We have a list of tasks and their periods. We might say, for example, period of task 1 is 20 milliseconds, or here's just a symbolic name. And then we have many other tasks as well. And typically you can find this information in design documents. In many DoD systems, you tend to see this table of tasks, and then you see sometimes the rates, or you can translate the period, or sometimes you actually see the periods there. So this is typically available. Then deadlines, that's another piece of information that you can find in software requirement specification, but not always. Sometimes this is not specified at all. Sometimes we have end-to-end deadlines. Sometimes there is no specification of deadlines, but there is an implicit specification of deadlines. Well, sometimes it's assumed that when we have a task, it needs to finish before it arrives again. So the deadline for a task is equal to this period. But this is another piece of information that we need to take as input. We do not require the deadline should be equal to the period. We allow you to specify a deadline to be any value less than equal to the period. So if you have a very tight deadline but a long period, from our perspective, it's fine if you write that down. We can analyze that. We need other things as input to the scalability analysis. One of them is execution time. So here you see execution time of task 1 is C1. That's just a symbolic name. It could be 2 milliseconds. And we have similar numbers for other tasks. And we actually don't mean execution time. What we mean is worst case execution time. This is an upper bound of the execution time of a task for all its possible inputs. And we also need to input speed of task 1 as a function of its co-runner. So one example here is that we describe the speed of task 1 if executed alone, and it may be 1. If the execution speed of task 1 when executed in parallel with task 2, then 0.6. And the fill in for other cases. So if we have this information, we can feed this into scalability analysis, which is a tool we have developed, and that will output these results. But we need to do more. We can ask, where do we get these? This we already get from documents. This we get to documents. Where do we get this from? And where do we get this from? Well, we have tools to do this also. So we have a tool that determines the worst case execution time of a program. And we also have a tool that determines the speed as a function of co-runner. And where do these tools, where do they get the input from? Well, they are based on the executable code, compiled code, not source code, but compiled code, and the actual hardware. So we don't deal with, we don't depend on a model of the hardware. We have the actual hardware and executable code. And we obtain these things experimentally, and then we feed this into a formal proof technique. So what we develop in this project, different things, but here are just a few of them that functions in this whole package of tools. We have one tool that does worst case time analysis. We have one that finds speed as a function of co-runner. We have one that does scalability analysis. And yeah, this is a new abstraction. that we created. The other things, C, D, and T, these are well-known quantities in literature, but this is something we had to invent. And we had to invent it so that we can actually analyze it. And we have done both. We have created this notion and we have created the analysis for that. And this is the thing that allows us to deal with undocumented hardware, because we are not describing the hardware. We're not describing how it works. We're not describing how many requests, how many memory accesses that the software system issues to the memory system. We're describing the effect of that on other tasks, on other cores. And then we are feeding that into SQB analysis. So I'm not going to go through all the tools, but just to give a view of what we have. Here you see one of the tools. It's a SQB analysis tool, and you can recognize some of these words here. You see a bunch of tasks. Task 1, Task 2, Task 3, Task 4, Task 5. We actually use a more complicated model here, or an expressive model that allows you to express a task as set of segment, but that's not so important now. And then we specify deadlines for each task. We don't specify period. We use something called minimum arrival time, which is a generalization of the period, but whatever you can do, it's more general and better. And we specify the tasks not just with a single C, but with C for different segments. So once again, it's more general. If you just have a single segment for each task, then it becomes the same as what I just said. And we specify which processor it's assigned to and which priority it has, and the speed as function of co-runners. And then you can just click the button here, and it will tell you if this system is safe from timing perspective. It will tell you schedulable, unschedulable. Schedulable means that for all scenarios, it will meet all deadlines according to the assumptions, and it will also output the response times. And this is a long discussion about how it works, but the main idea is that we run a fixed point iteration similar to classic rate monotonic, but instead of in classic rate monotonic, we have a closed form expression to compute the so-called request bound function of a task. Here we do it with solving a linear program. And there's a difference also in classic rate monotonic, you have request bound function per task. Here we have request bound function for the task and or its higher priority, and we have to obtain that by solving a linear program. But it turns out we can solve it very quickly, and it turns out we end up with the same complexity class as classic rate monotonic. So this is a generalization of classic rate monotonic, which is an important result. We also implemented the same tool in ADL because we see many DoD entities use ADL. I also mentioned that we need to do worst case execution time, and we have a tool for that. I talked about this 2 or 3 slides ago. And the main idea is that we want to find the input so that the execution time of the program is as large as possible. And that's a kind of like a black box optimization. And then we can borrow ideas from genetic algorithms. So in genetic algorithms, what we do have is that we have a population of animals or entities. And these entities or animals, they have genes. And then we can evaluate these, how good they are, and get the fitness. And then the genetic algorithms, what they do is that they simulate evolution. So eventually we end up with a population, we hope to end up with a population with many individuals with high fitness. That's what the genetic algorithms do. And we can see that we are trying to do something similar. We are trying to find inputs to the program so the execution time is as large as possible. We're trying to have a set of inputs so that we end up, so each input has a corresponding measured execution time, and we try to run a simulation of evolution to find a long execution time of a program. And that's what you see here. And it's been quite successful. We tested it here, and you can see it on the screenshot where we tried it on bubble sort. If you look at the basic textbook in algorithms and bubble, you can see bubble sort, and you can see that the worst case input should be descending elements and integers in descending order. For example, if you're sorting integers, then it would be the integers in descending order. And we try that, see what kind of execution we get if we have descending integers. And then we try to apply our tool, and what we found was that our tool actually yields longer execution time. So why is that? It is actually because our tool is smarter than the intuition of what you would get from an undergraduate textbook in algorithms. And it has to do with that different effects that influence execution. It's not just the control flow, it also has to do with some microarchitecture features. And our approach considers both of them. So that's why our tool can find an input that's worse than what a typical engineer might find. So it's better than human intuition. We have a similar tool to find the speed as function of co-runner, and we try to get the worst case slowdown depending on different inputs. We have academic publications also, and you see them here. We have a number of tools. Some of them I mentioned, and we have others that I haven't mentioned, but you can look at this link to download all of them. Some of them require third-party software in order to work, but many of them don't, so they are quite easy to use and get started with. And we had transition success also. We have interacted with different DoD entities, but one of them was AVMC, where we have shown them our tool, and they have used them internally and have seminars about our tools. So here's a team. We have an SEI team, and we also have collaborators at Carnegie Mellon campus and at University of California, Riverside. And here is my point of contact. So I'm happy to take questions. Thank you.